Hello everyone, I'm Ahmed and welcome to my 5th video lecture. So guys, how are you? Okay, so tell me in the comment box. So today another new topics, that is the density of unit cell. So density already have got in physics. So here I am going to write only the formula of density. Density is denoted by rho, or somewhere it is represented by small d, and it is mass upon volume. It is clear? Okay, this simple formula. So guys, in my last video lecture I talked about the 7 crystal system or 7 unit cell, and I told you to remember in a mnemonic form, that is C term THR, yes or not? Okay, so here I am going to write that is the C term THR. So here C for cubic already have got, and T for tetragonal, O for rhombic, M for monoclinic, T for triclinic, H for hexagonal, and R for rhombohedral. But here we have to discuss the density of cubic unit cell only, but the others unit cell or crystal systems are also here. It is not needed, so I am going to rough it. Okay. So again, cubic unit cell are 3 types. Already you have got. One is simple, or it is called the primitive, and this is called your FCC or CCP, and last one is your BCC. Here FCC means the face centered cubic spacing, CCP means cubic spacing, and the BCC means body centered cubic spacing. Okay guys, so here we have to find out the density of cubic unit cell. So to find out the density of cubic unit cell, we must need the mass of that unit cell and volume of that unit cell. Okay, so let me draw a unit cell here. Say it is our cubic unit cell. So it is our cubic unit cell. Okay, in this cubic unit cell we have got all the edge length are same here. Cubic unit cell, all the edge length are same, and I told it is A. So here I can write one thing, that is what? A volume of cubic unit cell. Volume of cubic unit cell, that is B is equal to A cube. And here it is said that the mass of the unit cell. How can we find the mass of the unit cell? So we can find the mass of the unit cell by knowing the effective number of atoms and the mass of one atom. If we multiply them, we will get the complete mass of unit cell. Yes or not? Yes. So here we have to find the effective number of atoms. So let us consider the effective number of atoms is Z. So here you write the effective, let here is a let the effective or rank of cubic unit cell. Cubic unit cell is equal to Z. Then what is the rho, density? Density is equal to, that is the effective number of atoms or rank of the unit cell or atoms of that unit cell into the atomic mass, If we multiply, if we know the mass of an atom, and suppose there is Z number of atoms, either it may be 2, it may be 3, it may be 4, it may be 100. If we multiply them, so we will get the mass of that unit cell. Okay, so Z into atomic mass divided by volume. So volume, it is represented by V, and in case of cubic unit cell it is the A cube. So I have shown here with V. Okay, so guys, here one thing, atomic mass. Can you say me the atomic mass of hydrogen, atomic mass of sodium? It's not easy. So everyone knows the molar mass of any elements. So for hydrogen, for sodium, for nitrogen, for magnesium, everyone knows the molar mass. So molar mass we know, but we have to find out the atomic mass here. Okay, so we don't require the molar mass here. We need the atomic mass. So we know that atomic mass AM, atomic mass is equal to molar mass divided by Avogadro's number. We know it very well. Atomic mass is equal to molar mass upon Avogadro's number. So here we have got Z into atomic mass. So in place of atomic mass, just you put the molar mass divided by Na. So here I will put that is the molar mass upon V into Na. So it's the density for cubic unit cell. And here Z. Put the value of Z1 for simple cubic unit cell and Z equal to 4 for face centered cubic unit cell or CCP, and Z equal to 2 for BCC, body centered cubic unit cell. Okay. So in most of the questions you are asked to find out the number of atoms. So density will be given, the molar mass will be given, Avogadro's number you know, and the edge length or the volumes will be given. So you have to find out the atomic number of atoms. Okay. So this is all about your density of the unit cell. So here you can mention one thing over here. You can write here. That is how can you write? You write here where Z is equal to effective number of atoms. You can write number of atoms or constituent particles. Okay. Here mm means molar mass. Here V means the volume. You can write here it is the volume of unit cell, and here Na means Na is equal to Avogadro's number. Okay. So this is all about your density of the unit cell. So now I put next heading, that is the position of voids. So here position of voids. Okay. Position of voids. Here only you have seen that in the three-dimensional packing we have to see tetrahedral voids and octahedral voids. Okay. So here we write in 3D packing. In 3D packing we have got tetrahedral and octahedral void. In 3D packing we have got tetrahedral and octahedral void. So here tetrahedral voids, it's formed by 4 atoms. It is formed by 4 atoms. Okay, whatever the voids form within the 4 atoms, this void is called your tetrahedral void. So this is your tetrahedral voids. And octahedral voids is something like this. It's formed by 6 atoms. So you could just put the other atoms like this way. Okay, it's something little distorted. Okay, put like this, and you will see whatever the voids you have got here. So this void is your octahedral voids. Okay, this void is your octahedral void, and tetrahedral voids is something looking like this. Okay, you put your tetrahedral voids is something like this. This is your tetrahedral voids, and octahedral voids is something like this. This is your octahedral voids. I have shown already tetrahedral voids and octahedral voids. So this is your tetrahedral voids. It's a look something like this. Exactly, you see here. Suppose your tetrahedral voids is formed between the 4 atoms. This is the inner atoms, pink color. This is the inner atoms, and above them there are 3 atoms. So you have to see here the voids, and the shape of this voids, it's exactly this one. Okay, just you consider this one. Okay, here you see. For this last atom, you just consider this vertex, and for 3 atoms the 3 vertex are there. Okay, so this is your what's called tetrahedral voids, and the octahedral voids is formed between the 6 atom. So here you have to see the voids. I think it is visible, yes or not? Okay, so whatever the voids formed between these 6 atoms, so this is your octahedral voids, and octahedral voids is something looking like this. So I have shown here. Okay, it is clear now. You see here So this vertex you can see, just you see this one, this atom. For these atoms you consider this vertex, and for this red two balls you just consider these two vertex. And at the back side of these three balls, there are three balls. Just you see its vertex are again, you can see here its vertex is upward, but it's below, its vertex is downward. You can see here it is also like a triangle, no? It's like a triangle, its vertex is downward. So it is called your octahedral voids and it is called your tetrahedral voids. But here the question or the topic is to find the position of the voids. How you will get the tetrahedral voids and octahedral voids? So for in case of if you consider the FCC or hexagonal close packing, HCP. Okay. So if we first layer, suppose we have taken the hexagonal 2D hexagonal close packing, and if we put the second layer, we will get the two types of voids. One is tetrahedral voids and another is octahedral voids. But when you put the third layers over the second layer, if you occupy the tetrahedral voids, then the lattice or the whatever the unit cell will form, that will be your HCP, hexagonal close packing. But if you occupy the octahedral voids over the second layer, then whatever the lattice or you can say whatever the unit cell form, that is your FCC or CCP. Okay, so here I will take the FCC or CCP, and we will see that here the tetrahedral void is located and where the octahedral void is located. Okay, okay. So here I will write here that you write like this way. In case of FCC or CCP. In case of FCC or CCP, so here let me draw the CCP here. So this is your CCP, say, suppose. Okay. This is your face-centered cubic close packing or cubic close packing simply. So here we have to see, suppose you consider the one corner atom. This, with respect to this corner atoms, there are three phases. Yes or not? This one phase, it is another, and backside another. Just to consider this one, this is your FCC. Okay, this is what? This is FCC. And just to consider this atom. If you consider this atom, with respect to this atom, you see here one phase, here another phase, and here also you see another phase. So three phases are there, and the three atoms are also there. 1, 2, and 3. And these three phases atoms, they directly touched with this atom, corner atom. Yes or not? Just you can imagine one thing. If the three atom touches over to this atom, you can see here one void is generated here. Okay, you see here one void generates. So it is exactly like this, no? It is exactly like this. Suppose one atom is here, and three atoms directly touched with these atoms, and you have to see one void, and this void is what? This void is your tetrahedral voids. Okay, exactly, it is your tetrahedral voids. And this tetrahedral voids, where will they get? You see here, we have got tetrahedral voids here. Something you can just imagine, we have got inside these three balls. Okay, so if you put a needle to this ball, from this ball to this ball, so if you put a needle, so it will become a body diagonal. Okay, so in that body diagonal you will see that the tetrahedral voids you will see here, and another tetrahedral voids you will get here. That means in each body diagonal there will be two tetrahedral voids. Okay, so you see here, suppose this is our room. So if I suppose arrange my hand in this position, then this is our what? This body diagonal. Okay, so you will get the tetrahedral voids here and there. Similarly, in this direction, there will be two body diagonal. One tetrahedral voids I will get here, and another tetrahedral voids I will get here. Again, here also. Here also. So how many body diagonal will be there? There will be total 4 body diagonal, and each body diagonal have 2 tetrahedral voids. Then 4 body diagonal will have the 8 tetrahedral voids. Yes or not? Here you see. Okay. Here you see one atom is here, another here, another is backside. You can see here it directly touches, and you can see it is something looks your tetrahedral voids. Okay. So it is your body diagonal. It's your body diagonal. So here you will get one tetrahedral voids. Here also you will get another tetrahedral voids. So at what position? Let us set the position of the voids. At what position you will get? Okay, just a body diagonal. I will put here the body diagonal. So this is our body diagonal. And we know that the body diagonal, it is your what? It is your 4r. This is 1r, r. So here we have got 4r. So 4r is equal to, we have got in case of body diagonal, that is root 3a. Yes or not? Okay. You have used the Pythagoras theorem to find out the relation between edge length and the radius of the atom. Okay. So here 4r is equal to root 3a, or you can write here that is a is equal to root 3a by 4. That means each point, this point is your root 3a by 4. So it is your root 3a by 4, and it is also your root 3a by 4. That means the tetrahedral voids will get in this position, root 3a by 4 and root 3a by 4. Okay. And this position, in this position you will get the octahedral voids. Later on I will discuss this one. Okay, first let me finish this one. So how many body diagonal you will get here? This one, this is your another, and this is your another, and one you have put, and just you put another like this way. So total 4 body diagonal will be there. So total here you will get total 8 tetrahedral voids. Okay, so total tetrahedral voids you will get, tetrahedral void is equal to 8. Let me change this chalk here, and octahedral voids is equal to, okay, now see octahedral voids. Already I told that octahedral void is deformed by the 6 atoms. Okay. So here you see I have taken the 6 atoms, and whatever the voids generates here, that voids is your octahedral voids. Yes or not? Okay. Now you can imagine one thing. See how many atoms is there? One atom is here and this here. 2. Below, above. 4. This side and in front of you. How many? 6. So whatever the voids will form between these 6 atoms. You see here? Between these 6 atoms. Okay. So that void will be your octahedral voids. So we have got one octahedral voids here, 1, and you see the edge length. In the edge length, just you see the gaps here. Okay, you have seen here the gaps. Okay, now you see here one atom is here and this here. One is here, another will be above because another unit cell will be there. Okay, simply just you understand. This is the edge length. To occupy this edge length, we need the 4 different unit cell. One unit cell will be here, another 2 unit cell will be here. So as a whole, it will occupy complete edge length. So just to consider one atom here, another here. One is below, another will be top. One is here, another will be again in this level, same plane here. So how many atoms? 1, 2, 3, 4, 5, 6. So that means whatever the voids form, it is a part of octahedral voids, but it is not 100% octahedral voids. Okay, that means we have the 4 unit cell here. That means whatever the octahedral voids we have got, it is only 1/4 part comes to this unit cell. Okay, so how many edges are there total in this unit cell? Just to count: above 1, 2, 3, 4, below 1, 2, 3, 4, here 1, 2, 3, 4, 12. So here we have got plus 12, we have got, okay, 12 into its edge length. In each edge length there is only 1/4 part of the octahedral voids. So I have to write here 1/4. So if you cut it, you will get 3. That means 1 plus 3 is equal to 4. That means octahedral voids in this unit cell is 4 and tetrahedral void is your 8. Okay, so again you can conclude one thing. What you see here, suppose let us consider, so I want to write here, if number of atom is equal to say n, then we can write tetrahedral voids is equal to, it will be twice n. Here you've seen that in FCC how many atoms are there? There are 4 atoms. So if FCC have the 4 atoms, we have got octahedral void 4, but tetrahedral void is equal to 8. That means double of 4. Okay. So here simply we can write, if the number of atoms for any unit cell is n, then the tetrahedral voids will be twice n, and octahedral voids will be your n. If you consider n, then octahedral voids will be n. If we consider number of atoms is n, then tetrahedral voids will be twice of n. Finish. So this is about the position of voids. So in next class I will discuss the questions. Various questions will be there based on these 2 topics, that is density and the position of the voids. Okay guys, so if you like my channel, if you like my videos, then just don't you sit simply, okay, you use your thumb, you like it, subscribe it, and also you comment it if there is something mistake in my video. Okay, thank you.